We're going to be covering a little bit of background in natural language processing, just to kind of catch us up so that we can talk about RLHF, about how it's affected language models, and like kind of the state of AI and machine learning in general. It's kind of cool. It's been a cool real-world application of reinforcement learning that's really taken off in this past year. And so before we dive into it, we're going to talk a bit about natural language processing. I don't know, has anyone taken Samir Singh's NLP course as part of the graduate program yet? A couple? Okay, cool. I'm just going to give a brief kind of background of natural language processing, what it is, what it means. So natural language processing obviously is working with language, working with text. Classically, there are lots of tasks that we've used to measure natural language understanding and how well computers do natural language processing. Tasks like sentiment analysis of sentences, classification of sentences, question answering, text summarization, part-of-speech tagging, named entity recognition, and translation. A lot of the traditional methods for doing these things were rather rudimentary up until recently. Things like feature engineering, bag of words, which completely ignores the sequence of words that are going into your comment in. If you're here for reinforcement learning control, you're in the right spot. Bag of words completely ignores sequence order, just looks at words. We have n-grams, which takes into account kind of local order of sequences of words, hidden Markov models. More recently, recurrent neural networks, which is kind of like the initial deep learning approach for natural language because it handles these arbitrary sequence lengths well. However, recurrent neural networks had some problems. So the problem with recurrent neural networks, one was that they have a strong bias towards recent information. To kind of get around this, some initial researchers have proposed using an attention mechanism over the input to attend to different parts of the sequence with different weights instead of just looking at the most recent hidden state of the recurrent neural network. In 2017, researchers from Google proposed attention is all you need, which completely removed the recurrent neural network from the natural language processing, just using a self-attention mechanism is what they called it, to process all of the inputs at once. You learn layers to map inputs to keys, values, and queries that you can then use to formulate your outputs as well. So attention is all you need. This kind of self-attention mechanism was called transformers. That was what the architecture, the overall architecture of this model was called. However, this didn't quite get us to modern large language models. That came later when we paired these large transformers with internet-scale data. So we're talking about like massive amounts of text inputs trained on language modeling tasks, which I mentioned, or which I didn't fail to mention at the beginning. But language modeling is simply trying to assign a probability to a natural language utterance. So if I have a string of natural language, gibberish should be assigned a lower probability than a sentence that is grammatically correct. Maybe like factual or sentences that exhibit some kind of reasoning should also have slightly higher probability than ones that include falsehoods or things that are unreasonable, right? And so pairing these transformers with internet-scale data gets us large language models. However, people developed all sorts of large language models, called all sorts of funny things. We had BERT, we had Elmo. Olmo came out really recently, Llama, and ChatGPT. But ChatGPT was a little bit different from the rest of these. Your grandmother probably has never heard of these others, at least when she thinks of Elmo and BERT, she doesn't think of language models. But ChatGPT, I remember when my family kind of knew what ChatGPT was and heard the term language models, and they're like, what is this thing? So what was the difference here? What changed, right? I think there was a change somewhere. Let's go into what that change was that took us from having to take these pre-trained transformers, fine-tune them for downstream tasks to be able to ask a single model to do all of my tasks for me, and it works perfectly. Not perfectly, sorry. It's not perfect. It works well. I can ask it open domain questions like, what do you know about reinforcement learning? I can ask it to assign a sentiment to the sentence, what do you know about reinforcement learning? Part-of-speech tagging, translation, all from a single model. And what let us do this? Well, if we look back a little bit at our timeline, so we had self-attention, 2017. Shortly after, GPT-2 was one of OpenAI's early attempts to train a language model on a large amount of internet text. At the time, it was very cool. It It could actually generate text that didn't just look like language, but actually made sense sometimes, which was pretty impressive. They did their whole OpenAI staged release thing where they're like, oh, this is too dangerous to put out publicly, so we're going to hold it back, and then they eventually gave you the weights. And nowadays we think of GPT-2 as kind of this dumb, silly model that's less than 1 billion parameters, rather small. A couple years later, GPT-3, this actually started getting impressive. We had scaling laws. We were at the scale now where we could do few-shot learning, in-context learning, and had some really kind of impressive results starting back in 2020 from GPT-3. I also wanted to quickly mention, before we get to the end of our timeline, instruction tuning, which basically going from having to do something like few-shot examples where you show the language model several examples of a task being completed in its context and then extract an answer from it later. Instruction tuning enabled this kind of zero-shot learning where you just described a task and then it was able to complete a task without seeing any examples. This was done just by having a small data set of examples of a language model being given instructions, completing a task. You fine-tune it on this data set, and then it's able to kind of generalize to new tasks just because it's learned how to follow instructions to some extent. One example of this data set in this class of models was Flan from Google. But then, just a year later, we had ChatGPT coming out in December 2022. And what happened kind of in the middle here that was kind of the impressive thing that made this change, made this go viral, whereas the other ones didn't, was RLHF. So that's what we're talking about today, is RLHF. So what made that kind of, that large jump that impressed everyone, not only in the academic community, but also worldwide as well. So any questions about NLP or transformers stuff? It's been a pretty high level so far. So we're going to dive down into reinforcement learning for language. So 4 years ago, 2020, this is back GPT-3 was out, transformers were around, and natural language processing was really taking off and really impressive. But we still didn't really know how to do reinforcement learning for language, and it was still kind of considered kind of an impractical approach, right? We'll talk a little bit about why that was. So you guys are familiar with the classic RL setup. We have actions being sampled from our action space, executed in an environment, and then some kind of state or observation being received from our environment, and then a reward signal that we're able to optimize by training a policy. One of the things that makes natural language reinforcement learning for natural language rather difficult is a large action space. So in language, our action space is words or tokens, which are kind of parts of words. And most of the times, these large language models are trained on very large vocabularies of 50,000-ish words, somewhere between 30 and 50,000 words. And if you've done a lot of reinforcement learning, the exploration is a big problem in reinforcement learning. We put a lot of research into how to do exploration, how to thoroughly explore our state space. And that's really not practical when you have an action space of 50,000 discrete different actions. And when your state space is also very large, because your state space is composed of tokens in a sequence, you have your instructions, kind of context for what the task you're trying to complete is, plus the answer you've generated so far. It's combinatorially combined over your vocabulary space. You get this massive state space that you could sample from. It's infeasible to explore it thoroughly with this action space. And so that's one reason why RL for language was impractical. The other reason is because we don't have a reward function. There's not a clear and easy reward function to optimize for natural language. If you think about it, the kind of tasks you're generating often require natural language understanding to be able to give you a reward function. You have to already understand language pretty well to be able to judge how good the language is. You can't just have a human labeler sitting there while you're doing online RL rating each of your rollouts. So that's the first kind of thing that we're going to address is how do we use a reward function for RL? Where did we get this reward function for RL? That's a big part of what RLHF is. So the first paper that I'm familiar with that kind of proposes learning a reward function for natural language processing is fine-tuning language models from human preferences, came out in 2020. I wasn't familiar with this paper at the time. I don't think it got as much traction as kind of its follow-up papers. which we're learning to summarize from human feedback, and then the Instruct GPT paper that came out in 2022, training large language models to follow instructions with human feedback. But all of these kind of do the same thing, and that's let's use labeled annotated data to train a reward model to then use for RL for language. So how do we do that? I'm going to take you through kind of the high level of how this is done, and then we'll dive down into a little bit more detailed how RL works. Feel free to stop me at any time if you have any questions or anything like that. So, collecting human feedback. First off, the first thing we kind of do is we have some kind of task we want to complete, and we have data instances of that task. So let's use the example from that middle paper I showed in the last slide, summarization. These figures all come from that paper. So we have several pieces of text, and we want to generate summaries for them. We might fine-tune a language model on this data set to give us a good initial policy. So one of the key things that makes RLHF work is starting with a good initial policy. So we're going to fine-tune on this data set to do summarization. And then what we're going to do is we're going to have a human label. The human's not going to write perfect summaries. The human's not going to rate your summary from 1 to 5. The human's going to look at 2 summaries and then say which of them is better. And this just happens to be like a much easier labeling task for annotators in general, also less noisy than doing like scalar ratings as well. So we're going to label human preferences. We're then going to use those labels to train a reward model. This reward model usually is initialized with our fine-tuned language model with a scalar head to give us our reward. And what we'll do is we'll get the output of the reward model for the 2 different summaries we just labeled, and we will say we want the scalar value for the better summary to be higher than the reward for the unpreferred summary, right? So we're going to optimize our reward function to give us this with this objective. And then now we have a reward function, and we can just use PPO. We can do rollouts from our initial policy. Usually you'll initialize your policy from the fine-tuned version of your language model that you use to gather the initial data, and you'll do rollouts, label those rollouts with a reward, and then do PPO. There's a couple of other additional details that we'll dive into in just a moment.
Can you give some kind of guess on like what the scale is in terms of like the amount of data and like model size required for step 2?
Yeah, so let's see if I can remember off the top of my head. I think we're talking tens of thousands of human label preference pairs on, I don't remember what like the Instruct GPT size was, but I mean a lot of follow-up work has done this on like 7B models and stuff like that. Things like the internal industry models might be a lot larger, things on the scale of like 20 in like the tens of billions of parameters for their model size.
Tens of thousands of data points, so like for a company with lots of money, that's not that.
No, yeah, and like it's yeah, so it's not awful. However, usually this process is repeated multiple times, and so you'll get your next policy, and then you'll use that to label more data, and then train a new reward model and repeat the whole process multiple times.
So you don't just train one reward function, it's an iterative reward function.
Yeah, and like most of the academic papers I've seen, they usually just do one iteration of this because that's easier in academia, but in industry, and in a lot of these papers they mention that they do multiple iterations of this, and usually the annotations are coming from like there's whole startups that are around just getting you good preference annotations. Around that. So if you have like good quality preferences, you can do it with kind of smaller.
Can you get away with the cheap reward model, or does it have to be as strong as the model you're training?
That's a really good question. Off the top of I mean, the papers that I've referenced so far use the same size reward model as they do policy. However, you'd kind of hope that you could maybe get away with like smaller size models for some of these modules, right? And I think I've seen some work that looks at that and that tries using smaller reward models. Off the top of my head, I can't point you to them though. So that's a good question. Not sure. Yeah.
Just like mathematically, this is very different from say like actor-critic methods, but conceptually, there seems to be some sort of relationship.
Yeah. So the actor-critic like reinforcement learning just happens in this last step over here, where we have our reward model that's trained, and that's labeling our reward. And we're using that to do some kind of online RL or policy gradient. PPO is what they use in the paper. You could use actor critic. You could use all sorts of things. But basically, once you have the reward model, then you can do a rollout, assign it a reward, and optimize your policy. You could collect a buffer of rollouts and rewards, and then use that to optimize your policy. Yeah. Using whatever, like your choice of RL algorithm, whatever you'd like, some kind of policy gradient method, typically. Yeah.
Why
PPO?
Why not? Why not do an off policy RL? Why not do soft actor critic or something like that?
Because OpenAI did it first. That's why.
Did they say why? Like, is it because PPO reduces variance and updates and there's just a lot of variance, or?
I don't. From what I can recall, there wasn't any explanation in the initial papers for why PPO, and they definitely didn't show any results for any other algorithms for sure. We're going to get into like other algorithms a bit later, but I actually have not seen a lot of work in terms of just like other RL algorithms for doing this, right? Usually PPO is just like the de facto thing. People know that it works relatively well for a lot of cases, but it's definitely open research question if there's better RL algorithms to use that might be more efficient or something like that. Yeah.
How does the noise affect the performance of the model? Because you have multiple people to judge the output of your generative model. So you might have some noise because it's multiple people can have multiple different judges.
Yeah, different preferences, right?
How does this handle the noise and everything?
For sure. I do think, I think one of the intuitions is that labeling preferences will be less noisy than labeling like score for scoring each of them, for sure. However, you're still right, because different annotators might have different preferences, and so usually the way to solve that is just by being very explicit and training your annotators very well. In this paper, they didn't use like mturk to do this. They hired annotators internally to do all this labeling for them, and they trained them on what things they should prefer versus not prefer. So that's absolutely a good question, and that's kind of why there's this new market, and like companies like Scale AI and other startups are actually like totally founded or like focusing on providing these preference annotations from like skilled preference labelers, because to get you like really good quality data. Yeah. Let's dive down a little bit into like a few more details of how we might do this. First off, there's a couple of key insights that I kind of already mentioned, but I'll touch on again. One is that preference labeling tends to be easier than having humans write like expert output. So if you gave me a piece of text and said, write an expert summary of this, write a summary of this, that might take me a lot more time than just labeling the output of one. Also, like I mentioned, preference labeling is generally less noisy and a little bit faster than scoring individual outputs. So that's like one of the key insights here. The other one is that by training reward function, we can label new rollouts and do online RL, right? Without the reward function, you can't do online RL. You could do like an offline RL kind of thing, but you can't do policy gradient online without that reward function. And I guess one other thing that's worth pointing out is that we couldn't really train this reward function until we had language models to the point where they were capable of modeling that reward, right? And I don't think that really, the language models we were working with really were capable of that until fairly recently. We had language models that were capable enough to be able to model the reward and learn that reward modeling objective. There are limitations though, obviously. This is actually still a very expensive process. Like, we were talking about how like RL for language was kind of impractical, and there weren't really good ways of doing it because it was too expensive. It's still expensive. Like, we have a data set, we're doing supervised training on that data set, we're labeling with human annotators, training a reward function, and then doing reinforcement learning on our policy. And like I mentioned, usually you'll do this like multiple times. And so this is still a very expensive process, but the results kind of speak for themselves. Like, people think it's worth it, right? Although a good portion of what we'll talk about in a little bit is like how people have tried to come up with easier ways of getting similar results. So we'll dive down into that in a second. First off, let's talk a little bit more about how we do the reward modeling, how we learn the reward function. So we kind of already touched on this, but we're going to start by supervised fine-tuning a language model on some task. That task might be summarization, it might be instruction following in general, so that we have a good initial policy. We'll label preference pairs from that data. We'll generate multiple outputs and rank those outputs. And then we'll initialize a reward function from that supervised model plus a scalar head, and then optimize this preference loss. Which here, again, is the x is your input, y is your preferred output, and over here, y1 is your unpreferred output. And we're going to try to maximize the preferred over the unpreferred output for our reward function loss. This is a result figure from that summarization paper, just kind of showing that both model size and then the different colored lines are different data set sizes for the reward model affect this. So you asked earlier like how many data points we would need. This is how many data points you're training your reward model with versus the model size. So you see like roughly tens of thousands is what we're looking at. And we can kind of approach what they were referring to as a human baseline, which is just like what a single human would label as preference versus an ensemble of humans might be a little bit higher. If you notice, like these aren't great numbers. Like I don't know, I think we typically like would hope that our machine learning systems get higher numbers than this, where the best model here is getting like 75% accuracy on a validation set. But in general, like you mentioned, this is kind of noisy, and this ended up being good enough of a reward function to improve their summaries, right? The actual reinforcement learning itself, I won't dive too much into the RL, but there is kind of a key component that I haven't mentioned yet to make this all work. So again, we're initializing our policy from the supervised fine-tuned model. We're optimizing with the reward. We're optimizing using reinforcement learning, an actor-critic method, maybe PPO, some kind of policy gradient usually. But here's our reward, and there's something kind of extra happening here. The R theta is our reward function. X and Y are our input-output, and so our rollout is Y, and we're going to label that with our reward function theta. Over here, though, we have this additional term, which is a KL penalty that's trying to keep our current policy close to our initial policy. So let's talk a little bit more about why we might want this KL term to try to actually constrain our learned policy, our RLHF policy, to be close to what our initial policy was. And let's talk about why we might want that. So as I mentioned in a few slides ago, exploration in language space is very difficult. There are lots of tokens we might want to sample, and RL is kind of prone to like catastrophic forgetting and policy collapse, things like this. And so by having this KL term, it's allowing our policy to explore, but like only within the domain of our original pre-trained policy. Again, this comes into what we were talking about earlier, where we're like, we're assuming that we're starting from a pretty good spot. We're assuming that our pre-trained fine-tuned policy is initialized well, is trained pretty well, and we're just trying to get that extra little bit out of it. So we want to be able to explore within the domain of our original pre-trained policy, and using this KL term both prevents policy collapse and encourages the policy to stay in domain for the reward function as well. So it doesn't go out of the domain for the reward function and start getting kind of funky rewards. Any questions about the KL penalty?
Is this in addition to like the PPO penalty to just like not move by very much each update? Yeah.
So this is like just usually fed straight into your reward. You'll still, like for PPO, you'll still do your clipped advantage and stuff like that. This is just added to the reward, or I guess subtracted from the reward, this KL penalty, right? And this is pretty key in getting it all to work.
Do we know how heavy this weight is to be successful?
That's a great question. Actually, this will come up again in a subsequent slide, but oftentimes the answer is no. What's oftentimes done is you'll specify a target KL between your current and reference policy, and you'll adapt the coefficient based on what the current KL is and what your target KL is. And so you'll have like an adapted coefficient for this KL penalty is what you'll do oftentimes. Yeah.
If we already have the PPO penalty, then why do we also need this?
Yeah, so the PPO penalty is just preventing your policy from moving too much at once. And this is in addition to that saying we don't just want to not move too much at once, we also want to not move too far from our original policy ever, right? Yeah. Yes, and we are assuming that the pre-trained LLM is of sufficient quality to actually get this. Like if we use GPT-2 to do RLHF, it probably would not be that helpful. Like we wouldn't get improved results at all. So one more big problem, I don't know if anyone anticipated this, but we're using a trained reward model, and then we're optimizing using that trained reward model. We can easily overfit to it is the thing, right? The reward model is not perfect. Pretty much all the time, if you're doing RLHF, you'll eventually overfit to your reward model, and the true preference will start going down. So the way you think about this is we're trying to improve our policy's alignment with human preferences, and as a proxy for human preferences, we've trained a reward model. But that reward model is not perfect, and we'll eventually overfit to it, and it will diverge from what true human preferences are eventually. And there's lots of work that goes into, there's been several recent papers about how we prevent overfitting, how we have better reward models. Could we use ensembles of reward models? And that generally helps a little bit, like doing a reward model ensemble might help a little bit, but this is consistently a problem. And also, when do you stop training is another thing. Is if I've exhausted how good my reward model can get me, when am I going to stop training?
Is there any research on I know what is there anything, does anyone ever look at unreliable reward functions? If there's an ensemble, is there epistemic uncertainty? If it's if your ensembles have variances if they don't agree, can you weight that rollout less or something?
That's a really good question, and I have no idea, but that's kind of a cool idea. A lot of your ideas, the things that might come to mind, very likely haven't been tried. This has only been around for really popular for a year or less, and very likely many things haven't been tried yet, and there's lots of things to try. So a couple of implementation details. I'm not going to focus too much on these, but if you're interested, there are several implementations online, and you can kind of look and see the tricks that they do to getting RLHF to work, because there are each library kind of has its own tricks that you need to do to get it to work well. And so most of these tips come from Hugging Face's implementation details of RLHF with PPO based on their implementation. So yes, your policy and value heads will typically share the same base LLM, and you'll want to slow down learning rates toward the end. I'm just going to go through these. Reward model, you don't want to overfit on your preference data either, so typically just train that for one epoch. Initialize your reward head, 0 mean with this variance here, 0 bias. During the training of your reward model, you'll also want to continue normalizing your rewards to keep them mean-centered. We're just using a sparse reward. We're initializing our value head to 0. One kind of thing that this blog post in particular points out is that since we're doing rollouts, we want to end with at a reasonable spot, usually at the end of a sentence, and we want it's hard to constrain a language model to give a sentence by the 100th token. By the 100th token, I want you to have finished a sentence. That's a difficult constraint to do, a difficult search problem to do. So typically what they would do is just generate rollouts until they get one that has the end of a sentence but prior to the 100th token. We call this rejection sampling. We'll actually talk about rejection sampling a little bit more in a minute. Discount factor of 1, we're just going to call all of our actions in our rollout the same, weight them all the same. And like I mentioned, the adaptive KL coefficient to keep your KL in a desired range, maybe between 0 and 10. Okay. Any questions about, actually no, I have one more slide for this section. Open questions, there's lots, like we mentioned. Which RL algorithms work the best? Is the value head helpful? Is keeping the value head, is combining the base LLM with a value and policy head helpful? Is the bootstrapping with the value function actually reducing our estimated variance? How important is the online aspect of online RL? Could we use something offline? Could we use value-based RL? How can we prevent overfitting on the reward model? And honestly, not everything we've learned in RL transfers directly to RLHF, and that's primarily because we're dealing with a pre-trained model. where oftentimes the assumption in RL is that we're starting with a randomly initialized policy, we're doing random exploration, and that's definitely not the assumption here. So we're starting from a pre-trained model, something that already is reasonable, and we're exploring within the constraints of that pre-trained model. We also have a completely different state than we're used to seeing, a different observation than we're used to seeing. Instead of having kind of a different observation each time, our state is literally composed of like a history of all of our actions, right? And you could think of ways to leverage that to improve our LRL algorithms. We could do search over the state and stuff like that. By retracing our steps is much easier in this state than it is in something like a simulator or a physics simulator. Okay. So questions about like RLHF things that we've covered so far?
I have a question about like the open questions. Could you just say a bit about how folks might investigate this bootstrapping question? Or like,
Yeah. What I meant by that was just what I really meant by that was whether PPO is helpful versus just like a vanilla policy gradient that doesn't have the value estimate at the inside of your loss.
this is not asking whether the reward function is.
No, I was talking about the value. Yeah, the value head is what I was talking about there. Yeah.
So when you have your data for your preference pairs, is it usually single turn or multi-turn? And if it's multi-turn, do you reduce that to single turn data?
That's a great question. It's always single turn, as far as I've seen. Like, we're going to talk about multi-turn RL for language models at the end of the talk if we have time. But pretty much exclusively, everything I've seen in the kind of published academic stuff is single utterance.
Is there a reason for that?
It's easier. I mean,
Because the models you are RLHF now, like they have huge context, so why not just give them multiple?
I think we'll talk about this more later, but modeling preference for multi-turn is very different. Also, you need to have, like, because the reason you would do multi-turn, and just to clarify what this means, or at least how I'm interpreting your question, when you interact with ChatGPT, oftentimes you'll send multiple queries to it with the same objective. If my objective is like trying to get ChatGPT to write an essay for me, I'll say, write an essay about this, it'll output something, and then I'll try to get it to modify that in some way by doing an additional input, and then it'll output another essay, right? You could consider modeling those multiple turns, those multiple back and forths as a single instance, and then trying to like optimize that. But like we can't do that in an online fashion because we have this other user that we're interacting with. So we can no longer do online RL without modeling that other user somehow. Is one of the biggest reason why we can't do it. And not can't do it, why it's hard and why people haven't done it a lot. Is because like modeling that other user is hard. How you do credit assignment becomes a lot more difficult. So you no longer just want to use like a discount factor of 1 all the way through. What your state is changes because you have like kind of this idea of a multi-turn process. So it's just like a completely different kind of beast in that sense.
But you could do it with something like DPO.
Something like DPO. We'll get to DPO in just a second. You could do something offline. Yeah, that's what you mean. Yes, you can definitely collect the data set, do some offline RL. That is later in the slides. So I'm going to pause that conversation. We'll talk more about it later.
How about this RLHF in other modalities, like for example, to images or video?
Yeah. You mean like multimodal? Yeah, for sure. That's a really good question, and I don't know of any open source publications on that. Like obviously, I've read lots of stuff on multimodal models. But then, applying reinforcement learning to these multimodal models, while I'm sure you can, I haven't seen stuff that does that specifically. But that's a good question. In general, multimodal models, while they're getting better, are still a little bit, still struggle a little bit. But okay, let's talk about alternatives to reinforcement learning. I know that this class is we go to 320, right? Okay. This class is on reinforcement learning, but let's quickly talk a little bit about like maybe if we didn't want to use RL for this, what could we do? What are some RL alternatives to accomplishing the same objective? So one very simple approach, say I had a reward function and I wanted to improve my model just using supervised learning with that reward function. I could generate completions, remove the completions with low reward, and then supervise fine-tune on the resulting data set. That generally helps improve my outputs. However, it's throwing away a lot of data, and so it's not necessarily the best approach we might use. A similar approach that does take advantage of the negative data are called control codes. This is similar to the decision transformer, if you saw that paper, where we're going to condition our output with a token that specifies whether or not it should generate a good output or a bad output. So, for example, maybe I have the input, what do you know about reinforcement learning? A good output might say reinforcement learning learns a policy by optimizing rewards. I'm going to prepend that with like a few tokens that tell it to output a good output. And then maybe I also have an example of a bad output by just saying it's hard. That's not very informative, not really what we want to know. But what we do is we would do supervised training on both of these instances. And then at inference time, we would use the good token to generate good outputs. And this generally works better than what I described in the previous slide. We are leveraging both our good and bad data to do these labels. A limitation of this is we can't use, like, if we have a data set of human preferences, we can't use that directly on this because this is assuming that our good-bad labels are absolute as opposed to relative. If I had a bunch of relative labels from humans labeling preferences, if I tried using those directly and prepending good and bad tokens to them, there would be too much noise to kind of learn anything from that. So it kind of requires that your good-bad labels be like absolute in that sense. Also, these aren't scalar values. Typically, you have to you have to bucket it in some way so that you can express this with a token. And you're not doing any kind of online optimization here either. So just a really quick comparison with some of those methods. This isn't the most thorough comparison, but it just kind of gives a little bit of an idea. Comparing like supervised fine-tuning, control codes, rejection sampling, then RWR and AWR are types of policy gradient. And just kind of showing that you can kind of ignore the y-axis. It's the KL from GPT-3 output, which is kind of a questionable metric. The x-axis is the score of the output, where left is better. Conditional, which is the control codes, typically work pretty well on their data set. However, it's situational, doesn't always work the best. This was a pretty limited study, but I just wanted to show that like sometimes filtering or rejection sampling might be all you need. Sometimes control codes might be all you need. In general, though, they are quite limited. One popular method, which has already been mentioned, is direct preference optimization, which came out last year, kind of shortly after RLHF became popular, and this came as a kind of response to RLHF saying, hey, you have all that preference data and you're training a reward model to optimize a policy. Why not just train on that preference data directly? Let's design a reward to help us do that. So if we generate a bunch of outputs, label it as preference data, we're not going to train a reward model, and instead we're going to optimize our policy directly on a preference loss, which is this here. And basically what this loss is saying, we're going to pick it apart a little bit in just a second. Basically we're saying that YW, which is our preferred output, win, or Y win, and then our unpreferred output, YL, we want to maximize YW and minimize YL. This should look kind of similar to our reward model loss, which we saw before. So picking this apart a little bit, on the top here we have the log prob of the preferred output from the current policy, pi theta is current policy, over the log prob of the preferred output from the original policy, yref is our original policy at the beginning of training. And then the same thing for our unpreferred output from our current and original policy. And this is the loss function we try to optimize. And so this is, if we optimize directly on this loss function with our preference pairs, this paper, direct preference optimization, showed that you could get competitive results with doing RLHF without having to do any RL. And one of my favorite things about DPO is that it's very convenient. PPO generally requires you to have a reward model, your original policy, and your current policy, and maybe a value function if your value function isn't combined with your policy, all in memory throughout training. Like every single iteration of PPO, you need to use all of these different models to label different things. And all of these are a large language model, typically with different weights. You could maybe do it within adapters to make it a little bit more lightweight. But it's still large memory constraint. Whereas DPO, you need the reference probabilities, but you can calculate those at the beginning of training and cache them. And then all you need is the current policy in memory, and you you can just run that just with the current policy. It's much more convenient. There's far less hyperparameters to tune compared to PPO, and it's relatively stable as well.
And so there are no online rollouts.
No online rollouts. This is just using your preference data. So that's obviously a limitation, right? And DPO is kind of seen as like situationally very helpful, and situationally will be competitive with RLHF. However, as you mentioned, the limitations of it is that we aren't doing online RL, right? Which means we're generally going to have poor generalization. Also, we need to have preference pairs, whereas like if you happen to have something with a reward function or where we're receiving a scalar reward, that you can't optimize that with DPO. DPO just works with preference pairs, although there are many variants of DPO that exist for like ranked outputs or like a binary good-bad output classification as well. But yeah, I skipped this slide back here, but basically one of the key things in DPO was they showed that there's kind of this implicit reward function that you're learning when you're optimizing the DPO objective. And if you use this implicit reward function, you can restructure your loss to kind of have this, what they think of as a more intuitive loss function, where we're trying to increase the likelihood of your preferred output, decrease the likelihood of your unpreferred output, and then weight that by the error of your reward estimate. It's a good paper, though. You should read it if you're interested in it, from Stanford. Okay. Any questions about DPO before we move on? Yeah, Rush?
I was just curious as to why DPO works so well and something like unlikelihood doesn't.
That's a good question. My intuition for that, so unlikelihood would just be like, if you have a bad output, just like do gradient ascent on it instead of descent, which is like similar to what this is doing. However, one major thing is that we have this additional normalization that's keeping us close to our original reference policies and like only kind of implicitly weighting the loss by like how far we've moved from our reference policies, right? And I think that's the key thing in just making it more stable than something like unlikelihood. Unlikelihood could easily screw up your policy. I think that's generally what the one paper I've seen that tried unlikelihood, yeah, just saw that it was kind of more unstable, if that makes sense.
So they didn't use any KL penalty with unlikelihood?
Not the one I saw, yeah. But maybe doing something like that would be closer to DPO and maybe make it more stable like DPO. Cool. Okay, so we've been talking about RLHF. We've kind of questioned the necessity of the RL side of RLHF. Now we're going to question the necessity of the HF side of RLHF. And what that kind of looks like, people have been like, well, do we need humans to label this data? We have language models. Let's just use the language models to label preferences. And so RLAIF generally does the same thing as RLHF, but instead of using humans to label this data, we're just going to use a language model and ask the language model to give us preferences. And this original paper that did RLHF showed that it's pretty competitive with RLHF. Here is a win rate on 2 different tasks. So how often a downstream user preferred output from RLAIF versus RLHF. It had a pretty competitive win rate. However, in this scenario, the labeler we're using is much larger than the model we're training. That's kind of like, is this just distillation? Is this just doing what distillation is doing? Is this better than distillation? I don't know. How helpful is this actually if we're trying to improve state of the art? Not very. They also did look in, though, to what if we, okay, so that was with a larger model, but let's say we were using the same model. So let's use a similarly sized model to do the labeling, and we can still get some improvement. This is maybe analogous to like self-improvement or something, where you're like labeling your own data and then like relabeling your own data and training on it again. That's kind of what this is doing. And if you see, compared to using the larger model where RLAIF is winning on summarization about 71% of the time, here it's winning on summarization about 68% of the time, so like still pretty good, just using the same model you're training. And so this is kind of asking like, maybe language models are better discriminators. Maybe showing the 2 potential outputs in your input is an easier task than just doing the generation. But yeah, so there's this potential for, can we just use language models to kind of self-improve? The direct RLAIF is the same thing, but without training a reward model. You just label your outputs and then train on the preferred outputs and just ignore the reward model bit. Yeah, so that's this bit. Constitutional AI, it's a pretty neat paper from Anthropic that just took this a step further. Instead of just generating 2 outputs and asking the language model to decide which of the 2 is better, we're actually going to come up with a constitution of what output should look like, kind of like the instructions we would provide to our human annotators. And what we'll do is we'll get an initial response out of the language model, and then we'll ask the language model to critique its own output and then ask it to revise its own output based on our constitution that we've created, right? You might have a constitution, things that look like this. The data set they were using was called the helpful harmful data set from Anthropic, where you're trying to get outputs that are helpful but not harmful. And so a lot of their constitution looks like this, is like identify specific ways in which the response was like harmful, unethical, racist, sexist, or toxic, and then revise that out of the output. And so generally what they would do, each time they generated some text, they would randomly sample some of these critiques and then revise their output a series of times. And then you end up with like a good response, bad response, and then you can do RLHF or RLAIF on those the preferred and unpreferred responses, right? This was very helpful with the harmfulness, which you can imagine, like that's a lot of what the Constitution focused on, was like in preventing harmfulness, and so they were successful at that, at preventing the harmless, making the output more harmless, which is the y-axis. So all of what we've talked about so far is focused on this concept of alignment. What we're really trying to do is align language models with human preferences. And so like we've said, like maybe reward models are the way that we can kind of model this alignment. Maybe a constitution, like we just said, is the way we can model this alignment. But in general, there's some questions about like what is alignment. So I'm sure like many of you have seen this phrase before. I'm sorry, as an AI language model, I'm unable to complete your request. Is something we see a lot when interacting with models like ChatGPT or Llama, like anything that's been fine-tuned basically on like alignment data sets has some of these responses baked in. And this is usually in an attempt to like reduce the harmfulness as one of the, I guess, I'm not sure if it's focused on so much because it's just easier to measure, which is definitely is easier to measure, and it's also kind of a priority if you're trying to release a consumer-facing product. You don't want it to have these kind of catastrophic like problems that we've had in the past where like industry leaders try to release AI models to the public and then they just go crazy really quick. But there's lots of questions that come with alignment, and there's lots of research in it, and I'm not going to dive into it, but I just wanted to mention it here. Things like, what qualities do we actually want consumer-facing LLMs to have? Should these qualities be different depending on what the downstream application is? Who decides what is ethical AI? How do we make sure that the AI has good representation of the humans that are being served downstream? How do we democratize ethics? Should we democratize ethics? How much should we steer language models to be factual versus creative? I think in Microsoft's AI, they even have different modes, like creative versus factual mode as well. So there's all this how do we make the language model work the way a downstream user is going to anticipate it work? I included this here just because it's kind of an interesting quirk that a lot of models that have been trained with RLHF generally have longer outputs, longer responses. A lot of times you'll see people normalize the results by output length just because it's kind of an odd phenomenon. But artifacts like this definitely do exist. People do RLHF, you gather preference data, and then there's some weird artifact that that the end model exhibits. And the question is is that because we actually prefer that, or is that some artifact of training? Do we actually prefer longer responses? It seems like we do, but maybe we need to change the way we're doing the RLHF to prevent it from having that artifact. Okay, one last thing in alignment before we move on to our last section, and that is, what is RLHF actually training? So this is some interesting research that's come out recently, and there's been a follow-up work very recently that I didn't include in the slides. But basically what this work is kind of suggesting, and work like it, is most of the substance of large language models comes from pre-training data. And what RLHF is doing is just kind of unlocking that information from the pre-training data. And one way they use to kind of test this hypothesis is by looking at the change in probability from a pre-trained model versus the RLHF model on tokens in an output, right? And they found that the difference in probability is very large for kind of stylistic tokens, but actually smaller for more content tokens. And this is kind of in support of this hypothesis that says that alignment can be a simple process where the model learns the style or format for interacting with users to expose the knowledge and capabilities that are already acquired during pre-training. And there's been more and more support for this, people showing that you can just do in-context learning or few-shot learning and get decent results that are competitive with RLHF, just if you know kind of what to tune for. I think it makes a lot of sense for the content, and the real ability comes from pre-training. I don't think that's surprising at all. But yeah, can we unlock the alignment capacity of RLHF without requiring the RL? I don't know. But there's lots of work into whether or not we can do this.
Almost like you could have a supervised learned main model that has info, and then the one that actually present the info to the user could be way smaller and learning.
Totally. Yeah, absolutely. Okay, multi-turn RL. We got to it. We made it. This is the last section. And I only included it because I'm interested in it particularly. This is kind of what my research focus has been on. And it's interesting, it's hard, and hasn't been the focus of RLHF so far, but I think it definitely is becoming more prevalent, and I've seen more research being done in this area kind of to indicate its significance. So let's talk a little bit about what we mean by that. So as I mentioned before, although we've only been optimizing these language models for single turn, single utterance outputs, there's actually a lot of situations in which we might care about multi-turn outputs, specifically in conversational scenarios where we oftentimes are using ChatGPT almost as if it should be kind of more like a chatbot, but it's really not. It's really just looking at what your MET-last output was and creating the best output it can, not thinking about potential downstream things. You'll never see ChatGPT ask a clarifying question or do anything with the intent of it helping it produce output further down the road. That's what we'd like to do, right? if you're having a conversation with somebody, someone in a conversation might output an utterance. I might output an utterance with the intent of improving my utterances later down the road. But that's not the case at all for like modern language models, like vanilla as is. So conversational things like recommendation, chatbots, customer assistance, collaboratively creating content, programming, and this I mean like programming with an interpreter or with like unit tests, like being able to get feedback from a unit test or an interpreter and then continually and iteratively improving your output in a multi-turn scenario, like being able to query databases and APIs, playing games. A lot of my previous research has just come into, has become just getting language models to play games, because that's like one way to test like how we can do multi-turn stuff in a way that's easy to measure. So one indicator that this is something that's of growing interest is just the amount of benchmarks that have come out that try to measure this. So there's text games like Science World, where you're in a completely textual environment and prompting the language model to complete science experiments, and the language model has to interact with the environment using text alone and has to kind of get better as it goes. Agent Bench, which just has like, it has text games, it has card games, it has like database and executing, following instructions, interacting with a Linux terminal, all sorts of stuff, measuring language models' ability to do this multi-turn tasks. Smart Play, LMRL Gym, LLF Bench, which provides like natural language feedback instead of a scalar feedback, Travel Planner. And however, most of these are purely for evaluation and not for training. So the vast majority of these are used for evaluating language models and maybe improving them via prompting, but not for actually fine-tuning, like with online RL, like we were talking about. Like none of these use all online RL, with the exception of LMRL Gym being the one that actually does use their benchmark that they've created to do online multi-turn reinforcement learning and offline value-based reinforcement learning. So I want to talk about this really quick just because I think it's neat. It's kind of it just came out in November, and it's not perfect. It uses rather small models. It only uses GPT-2 and doesn't have like the most conversational tasks, but it is still pretty neat. So you have 10 total tasks. 7 are hard-coded things like following a maze, or navigating through a house that's described in text, or playing chess just with strings. And then 3 of them are language model-based environments, where the environment itself is also a trained language model, doing things like playing 20 questions with you, or trying to guess what city the other language model is from, the other user is from, or trying to sell a car at a car dealership. So these are some examples of conversational tasks. And back to your question, Roz, of like why this isn't done a lot. I think actually designing multi-step tasks that like we're very confident that require multi-steps is difficult. Like a lot of the things I described in the previous slides, while yes, occasionally, like intuitively, you'd assume that having multiple steps would improve results, you could also just train a language model to output the best result first in the first turn even better, which is normally what people have focused on. And designing tasks that kind of require multi-step reasoning or multi-step outputs is non-trivial, I think. And also, the most interesting ones in natural language generally require like using a language model as your environment, which is also questionable to some extent, right? And expensive and slow. So they did this though, trained on these different tasks with several different methods. Behavior cloning, which is like they had an offline data set for each of these tasks that they fine-tuned on. They used that to initialize all their other methods. They did rejection sampling on the offline data. They trained Monte Carlo value estimates and used that during decoding time, implicit Q learning. They did do online PPO, and then they did like an online rejection sampling kind of thing as well. The kind of conclusions that they got from this, or that I guess I've got from this, is one that online learning, they were kind of struggling to get it working. I don't know how much of this was just their implementation, or like not having done a thorough hyperparameter search, but it is generally harder doing online PPO. Also, if you notice, the TD estimates, which is the ILQL, generally did better on the, which you would assume does better. It has lower variance estimates and stuff like that. Did better on the hard-coded environments, but actually failed to do better on the more natural language environments. And the more natural language environments actually did better with the Monte Carlo estimates. So this is maybe just indicating that maybe it was because GPT-2 wasn't capable of modeling the value very well in a TD error scenario, or maybe it was because natural language is just hard. I mean, either way, I think it indicates that natural language is harder to model than kind of this format templated, hard-coded language. So there's lots of open questions in this area. Just to illustrate why this is kind of difficult, this is like an example of like a 20 questions task that you might have where like the first output is from the agent, and then the no's and yeses are from the environment. There's some hidden information here, which is what the object is, which in this case is a carrot. You might get a reward at the end. You could do some kind of discounted reward as you go, but then like kind of how do you do credit assignment for your different tokens in those as well? Because we kind of have this hierarchical thing going on where like our action space is the tokens, but then we have states that are high-level states in the different turns. It's just not immediately obvious what the right thing to do is, and naively applying PPO is difficult at times. So, are all tokens created equal? How could we improve these TD estimates? These are all research questions that I am interested in looking into. And I'd love to chat about if anyone has any ideas or something like that. But I'm actively looking into this stuff. Yeah.
So it seems like the biggest problem is you can always train this with another, here the environment is one of the agents talking to you, and that environment, will know information that your language model you're training doesn't know, for example, your observation, your next observation or something. Or for ChatGPT or something, it's general. There's no scenario where it really knows that it can gather new information from a human just because that's not how it's trained.
Right.
And maybe maybe if you could cluster the training data you have into topics, you could train a language model with topics held out, and then you can train it interacting with language models that were trained on those topics or something. There could be some kind of training machine where you actually teach it in a general way that there may the other user might know information you don't or something.
Yeah.
Some kind of training machine with it where if they ask a question you don't know it, you can learn to ask.
Yeah, absolutely. Yeah. I've been trying to consider kind of tasks in which there is definitely some hidden information that needs to be uncovered in a non-trivial way. That's not just asking for, tell me all your preferences so that I can output the essay you want me to output or something. Yeah. But yeah, doing it in topics like that might be interesting. Yeah.
In the previous slide, what is the GPT-4 column?
The GPT-4 column is just using vanilla GPT-4 with some prompts on these outputs. If you notice, it does actually pretty well on a few of these, better than the other methods on the natural language ones, right?
Yeah, and then 0 for chess.
Yeah, because, did you see what chess looks like? It's just like a string of characters, and that's all you give GPT-4. It's not able to play chess like that. You could fine-tune GPT-2 to do that, but even something like GPT-4 can't quite do that, and just without the additional natural language. So they kind of included that for completeness, but their main goal was to show how they could train a language model to do this task, right? But yeah, anyway, interesting stuff, and definitely worth looking into. So we have now a brave new model that's been RLHF'd. We have this new method. I was curious, and so I plugged in some terms into Google Trends to look at Google Trends over time. RLHF and large language model. You can see where ChatGPT came out. It kind of just started taking off. And a lot of this can be attributed to RLHF and this whole research direction. I also happened to include, I was trying to look for other terms that kind of were correlated with this, and I found another term that was correlated, and that was AI risk, which I thought was interesting. So the search term AI risk took off right about the same time as ChatGPT. The spike there is when the Center for AI Safety did their statement on AI risk, that statement on AI risk that was passed around a whole bunch. but yeah, just interesting. Just wanting to make the point that this is an impactful technology, and there's a lot of work to be done on it in a lot of different sub areas. So, some research directions to wrap this up. This is my last slide. We talked about the fact that really people haven't explored like what RL algorithms are the best for language models. It usually is just defaulting to PPO. Maybe something value-based would be more interesting. Maybe you don't need the full PPO. Some kind of more vanilla policy gradient would be fine. Reward modeling. How do we take preference data and model it as a good reward function? Do we use ensembles? Do we use a smaller reward model? What are the constraints there? Using preference-based loss functions like DPO, can we look more into that? Kind of eliminating RL from the equation. When do we need RL versus when do we not need RL? It's not really clear right now, like in what situations is DPO sufficient versus RL. In general, like if you have a lot of data coming in, DPO might be sufficient versus if you have more limited data and you need to kind of get every last bit you can from it, RL might be more important. AI alignment, ethics, and safety, multi-turn RL. A couple things that I didn't mention earlier, value-based decoding. If we learn a value function, we could use that value function to improve our results. Everything I've talked about so far has just been sampling from our learned policy to do rollouts. But if we learned a value function via like offline RL or value-based RL, or even like our PPO value function, I've seen people do this as well, we could use that to improve our decoding process with like Monte Carlo tree search if we've got the time for it, or some more like kind of greedy method like A* or something like that. And then learning from natural language feedback instead of using scalar rewards, like if a human told ChatGPT, like, no, that's actually not what I meant, I needed you to do this, that was a bad thing that you did, bad language model. Like, could that be more helpful for doing this RLHF? Also, could we come up with a name that's more broadly encompassing than RLHF so I don't have to refer to everything we've talked about today as RLHF when really not all of it is RL, not all of it is HF. But yeah, that's it for today. My name is Colby Nottingham. You can find me on Twitter. I sit upstairs on the 4th floor all day long. If you want to chat, email me, let me know. I'd love to chat about this stuff. So yeah, that's all.